We are. My name is Octobre Cornea. I'm the director of the Centre de Recherche Mathématiques, and I'm very happy to introduce this lecture today. So, this is a lecture that will be given by the winner of the Prix Aisenstadt Prize. This prize was founded in 1991, and it recognizes important contributions to mathematical research by a young researcher working in Canada. And young for this purpose means less than 8 years after their PhD. The prize is decided each year by the International Scientific Advisory Committee of the CRM, and it's extremely competitive each year, which is proof that Canada hires very strong mathematicians from everywhere. And, for 2022, the prize is awarded to Yevgeny Liokumovich. Did I pronounce this right? I practiced today a few times. He is from the University of Toronto. The prize is awarded to him for important contributions to geometric analysis, in particular for his proof with Marques and Neves of a conjecture of Gromov. Liokumovich obtained his PhD at the University of Toronto in 2015 under the supervision of Nabutovsky and Regina Rotman. And he was a Nuremberg lecturer at the CRM in 2020. And he was awarded a Sloan Fellowship in 2021. So we're very happy that he's back with us here. And he will speak about new isoperimetric inequalities and their applications to systolic geometry and minimal surfaces. But before he can speak, I want to give him the medal. So the Eisenstadt Prize comes with a medal, and I will be happy to present it to Yevgeny. So I think we need a picture, and I'm glad to have this pleasure to present the medal.
Thank you so much. It's a great honor, and I'm very humbled. Thank you for having me here. I'm going to talk about some new isoperimetric inequalities and their applications to problems in geometry and topology. The isoperimetric inequality has a very long history. According to Virgil's Aeneid in 8th century BC, almost 3,000 years ago, Queen Dido had an arrangement to deal with King Berber that she can get as much land as she can enclose with a piece of bull skin, an ox hide. So obviously the king didn't think she'll get much land, but what she did was she cut the ox hide into tiny, tiny strips and made a very long rope with it. And then she encircled with that rope area of maximal area, as much area as she could. So she had to solve an isoperimetric problem to find a way to enclose maximal amount of area for some given fixed amount of boundary. And of course, the best way of doing that that she found was doing it with a circle. So disk is the maximal amount of area for a fixed amount of boundary that you can get. And that was almost 3,000 years ago. This is Queen Dido on 10 Venetian dinars bill, right? And then, of course, the story is that on that spot, she founded the city of Carthage, which is located where modern Tunisia is, in modern Tunisia, that part of Northern Africa. And this inequality generalizes to higher dimensions. If you're given a set in Rn, then, and you ask, well, how much volume can I enclose if I fix the boundary area of that set? And so the amount of volume that you can enclose is bounded in terms of the size of the boundary. And the best thing you can do is to consider a round ball. That's when this inequality becomes a quality. right? So you can control the amount of volume inside in terms of the size of the boundary. So this is a very important inequality in mathematics. It plays a crucial role in functional analysis via its connection to Sobolev inequalities. It plays a crucial role in spectral geometry. Today, I'm going to talk about a relative of this inequality, a different version of the isoperimetric inequality for manifolds of higher codimension. So here we are considering n-1 dimensional boundary and an n-dimensional interior. What if instead we considered a curve in R3? This is our curve C. It's one-dimensional set, and we are in some larger dimensional space, and we ask about the relationship between this boundary and various embedded disks with that boundary. Of course, we cannot, in general, control area of any disk with that boundary. The disk can be very large. We can make it arbitrarily large. However, maybe a better question is about an optimal filling of this boundary. So say we want to find a disk with as small area as possible, whose boundary is this curve, some filling with small area. Can we always find a filling of a given submanifold so that its area is controlled in terms of the size of the boundary? So this is a higher codimension of this talk today, and it will appear in several episodes, and we'll see how it's connected and has important implications in different problems in geometry and topology. So this is the version of the inequality due to Michael and Simon, but various generalizations of this inequality were proved by other people. And I guess this list is not exhaustive. There are other people who proved inequalities like that. So in this inequality, we control the size of the filling. We know that there exists some filling whose size is controlled in terms of the size of the boundary. Are there any questions about this inequality? Right. So the question about the constant is an excellent constant. So it's an excellent question. So Feder-Fleming proved this inequality with the constant C depending on the ambient dimension n. It was later improved by Michael and Simon so that it only depends on the dimension of the submanifold K. And that's actually a crucial difference that we'll see in a moment. I'll explain why this dependence is very important. Later, Almgren proved this inequality with optimal constants for area minimizers in Rn, and these optimal constants will be the ones that realize the disk, so that they will be the same inequalities up there, but the results of Feder-Fleming and Michael Simon are worse inequalities. And Gromov proved this inequality in infinite dimensional Banach spaces where the constant is not optimal. And then Wenger gave a simpler proof of Gromov's result, and Simon Brendel proved an inequality that is optimal in codimension 2, but not optimal in general, but applies to some other situations, to minimal surfaces which are not necessarily minimized. Okay, so the first episode in which we'll see how this inequality has is very useful is systolic geometry. Systolic geometry studies the problem of the geometry of non-trivial minimal submanifolds, and in particular, if you consider the length of the shortest non-contractible loop. So consider, for example, different two-dimensional tori with different Riemannian metrics. That these are all tori, but they have different geometry. And you can see that, so these two have these tiny, small, non-contractible loops. So they have small systole, and this one and that one have large systole. The length of the shortest non-contractible loop is large. And so you can try to understand the relationship between this length of the shortest non-contractible loop and the geometry of the manifold. And if you stare at these examples are actually from an excellent paper, overview paper by Larry Guth, Metaphors in Systolic Geometry, but this got hidden. You maybe will make a conjecture that there should be a relationship between the area of the manifold and the systole, that the systole of the torus should be controlled by some constant, depending, some constant times the area, this torus. And of course, this inequality should be scale invariant, so we'll take the square root of the area. And this is indeed the result that Lohner proved in late 1940s. And later, a student of Lohner, who proved in 1950s that a similar inequality can be proved by RP2, for RP2. And then for a long time, there wasn't much progress on this problem. People were, Berger, for example, popularized this question, trying to prove similar inequalities in higher dimensions. But the high dimensional metrics are much more wild. And Gromov got interested in this question. And initially, he wrote that he thought that if it's true, it's such a simple fundamental inequality, there should be simple proof. And when he didn't see simple proof, he thought that it should be wrong and there should be a counterexample. And so for some time, he was trying to look for a counterexample, but then eventually he proved the result. So the result is that for a very large class of topological manifolds, for any Riemannian metric, the systole is controlled in terms of the volume of the manifold. Right? So we do need to put some topological constraint, because for a sphere, for example, you cannot talk about the length of the shortest non-contractible curve. Every curve is contractible. And essential manifolds is a large class of manifolds. They include all spherical manifolds, manifolds with high homotopy groups equal to 0. So in particular, negatively curved manifolds, tori, RPN, or if you take any manifold and take a connect sum with an essential manifold, you'll get an essential manifold. So for all of these manifolds, the systolic inequality is satisfied. And Gromov's proof is really beautiful and non-trivial. The proof relied on the following two observations. So the first one was an observation that if we can embed our manifold in a particularly nice way into ambient space, for example, into some large dimensional Euclidean space, we can embed our manifold M. And if this manifold M is equal to the boundary of some, so this n-dimensional manifold, n plus one dimensional manifold N, such that N is contained in our neighborhood, then the length of the shortest non-contractible loop in M will be controlled by a constant times this R, bounded the systole in terms of the feeling radius of the manifold, the size of the neighborhood in which we can manifold M. And it's a rather beautiful topological argument for why this holds. It's an argument by contradiction. If this is not, then you can basically extend, you can find a map from N into M, which will be identity on the boundary. And that's impossible for topological reasons. And the second observation is that if you want to bound the feeling radius, then you can use isoperimetric inequality precisely of the type that we stated in the beginning. So if you have some boundary Z and you want to find a feeling that's not too far, well, suppose the feeling goes very, very far away. That means that it has these long fingers. And then you can start cutting those fingers and replacing them by minimal feelings. And by query inequality, the cuts will be very tiny. And so by the isoperimetric inequality, the feelings will have very small area. And by combining query inequality with the isoperimetric inequality, you will get a contradiction. You can show that the fingers should not exist. So this is similar to the intuition behind monotonicity formula for minimal surfaces. Minimal surfaces do not have long fingers. They should have, they should grow fast, because otherwise you could just cut and replace with something of smaller area. But the difficulty here was that, okay, so the plan is like this: how to put these two observations to prove the theorem. First, you embed your manifold into some nice space. Then you apply isoperimetric inequality in that space, and you are done. You prove from the isoperimetric inequality, you prove the filling radius inequality, and from the filling radius inequality, you get the bound for the system. However, manifolds don't embed isometrically into Euclidean space. And by isometrically, we mean not in the sense of Nash, but in the sense of distances in the ambient manifold actually being equal to the distance on the manifold. However, there is a very nice embedding from the manifold M into the space of L infinity functions on M. This is known as the Kuratowski embedding, where each point X is sent to a function which is just the distance from X. And this inequality turns out to be an isometric embedding into this infinite dimensional Banach space. And so Gromov proved an isoperimetric inequality in the infinite dimensional Banach space, which implied the filling radius inequality, which implied the systolic inequality. So this was Gromov's proof from the 1980s. Larry Guth asked if Gromov's result can be extended to a different setting where we replace volume with Hausdorff content. So Hausdorff content is not maybe a very well-known quantity, but it's actually somehow a more simple and more fundamental quantity than volume. So how do we define volume? Let's remember the definition of Hausdorff measure. So we consider different coverings of our sets by balls, and we sum up radii to the power of n for these coverings, and we take the infimum. And then we take the size of balls with which we are covering. So that gives us volume, Hausdorff measure. And Hausdorff content is doing something simpler. We're just considering all possible coverings by balls of any size, and we take infimum over that. So this is a simpler procedure. And by definition, Hausdorff content will be smaller than volume. And also, if your set space is compact, then Hausdorff content will be finite, right? So you have a three-dimensional space. The two-dimensional volume of your space will be infinite, but the two-dimensional Hausdorff content will be finite. Unfortunately, it's not a measure. That's its. If you have a space of dimension n, Hausdorff content of dimension n can be very useful if you would like to ignore small wrinkles on your manifold, things that are happening on small scale. So imagine a very, very long and thin torus of small, very small width, to which we attach many, many tiny hyperbolic surfaces. So we do the connect sum operation with many, many tiny hyperbolic surfaces of huge area. So this long torus will have very large area. However, it will have small two-dimensional Hausdorff content because it kind of looks one-dimensional. If we just cover it with balls of radius larger than this tiny hyperbolic surfaces, then when we sum up the radii squared, we will get quantity that's maybe compared to 1, whereas its area could be 10 to the power of 10. So Hausdorff content often appears when you'd like to ignore things that are happening on small scale. And so it would be very nice to have inequalities that tell us that that strengthen the relationship between volume and other geometric invariants by replacing volume with Hausdorff content. Because for the systole, it actually doesn't matter if you have a lot of wiggliness on a small scale. That doesn't prevent appearance of small closed geodesics, small closed curves. In fact, it somehow should help that. And so Larry Guth conjectured that Gromov's inequality should be true if you replace volume with Hausdorff content. And this is something that we proved with Boris Lishak, Alex Nabutovsky, and Regina Rotman a few years ago by first proving an isoperimetric inequality, where instead of volume, we have Hausdorff content. And this is a very general statement, which doesn't even somehow look like isoperimetric inequality, but the proof is very closely related to Gromov's and Wenger's proof of isoperimetric inequality in Banach spaces. So we start with an arbitrary metric space X. Now, an arbitrary metric space X doesn't have a good notion of a boundary, but instead of boundary, we just use any closed subset. So this is our boundary. And so we have some map of this boundary into our Banach space. And then we claim that we can fill that boundary, basically find F from X into B, which is an extension of this little f. So the restriction of F to Y is equal to F, so that the n+1 dimensional Hausdorff content of the image is controlled in terms of the n-dimensional Hausdorff content of this boundary in our space. And as a consequence of this isoperimetric inequality, we also obtain a new systolic inequality, which generalizes Gromov's systolic inequality. So given a manifold which, now this is a more general statement, which depends on the dimension M. When the dimension of the space is equal to, Hausdorff dimension of the space is equal to M, then we get a generalization of the systolic inequality because Hausdorff content is smaller than volume in that case. But if M is a different number, smaller than the Hausdorff dimension of the space X, then we get a completely new systolic inequality that applies, for example, so a space like T2 cross S2 is not essential, but it is too essential. And so we do get a bound on the systole of the space in terms of now the two-dimensional Hausdorff content of the space with some metric. And I'm sorry, I haven't defined what M essential is. It's a little bit technical. Basically, you look at the map into the Eilenberg-MacLane space with the fundamental group of X, and the induced map on cohomology or homology in that dimension is non-trivial. That's what it means to be essential. Or more generally, the space doesn't factor through a smaller dimensional polyhedral complex. I need to watch time. So let us now go, are there any questions here? So let us now go to the second episode, which will be about minimal surfaces and the space of cycles. Construction of minimal surfaces is also a problem with long history. The kind of minimal surfaces that we've seen in the first episode were one-dimensional minimal surfaces, which are also known as geodesics, so the curves that minimize length. But you can generalize this notion to high-dimensional objects, right? So you can think about, for example, this is S2, and you can think about an equatorial circle, but you can also try to imagine this picture one dimension larger, where this is S3, and this is equatorial two-sphere. So this equatorial two-sphere would be an example of a minimal surface. The property that it has is that locally in a small ball, it minimizes area among all variations of this portion with fixed boundary. Globally, however, it does not minimize area like you can imagine pushing the equator down and its area will go down. However, it is a critical point of the area functional. If you look at these variations, the derivative of the area with respect to these variations will be 0. So minimal surfaces are critical points of the volume functional. And a very fruitful idea to find critical points of functionals was to use topology of the space. So imagine that this is how the infinite dimensional space of k-dimensional submanifolds looks like. It doesn't actually look like that way, but let's imagine that this is how it looks. And so we would like to find a critical point, a saddle point over here. And so one way we could do that is we could consider these loops, these non-contractible families of submanifolds, and we could try to minimize the largest volume in this loop to kind of pull this loop down. And the place where it will get stuck will be precisely the saddle point. So this is the kind of mountain paths or min-max or Morse theory statement that you often see in differential equations. And it has been successfully applied to minimal surfaces, although the story is quite long and there are many technical details about how this can be done. But the upshot is that it was most successful in the case of codimension 1 submanifolds, where it was proved that through works of many people, starting with Almgren and more recently due to Marques, Neves and their students and collaborators, there are infinitely many distinct minimal hypersurfaces in compact manifolds. And they're smooth up to dimension 7, and in high dimensions, they have some small singularities. And in my work with Greg Chambers and also work of Antoine Song, we extended this result to manifolds of finite volume or non-compact manifolds satisfying other conditions. And then similar techniques were applied to by Shinju and Jonathan Zhu to manifolds of constant mean curvature and prescribed mean curvature. So let me go now a little bit through some details of how this construction goes, and then I'll try to steer our course towards the main character, the isoperimetric inequality. So this mountain pass idea, how does it work? So the idea is that we start with non-trivial topology. We pick an element in the cohomology of the space of submanifolds. So this is a space of flat cycles, space of submanifolds of varying topology. And we consider those families that lie in that topological class, that correspond to this non-trivial cohomology class of the space. And then we pull this family down. We try to make the maximal volume in this family as small as we can. And so then the claim that this infimum of the supremum, this minimum of the maximum, will be the volume of a minimal submanifold. Now, this min-max characterization maybe reminds you of the min-max characterization of the eigenvalues of the Laplacian. So instead of volume there, we have the Rayleigh quotient, the integral of the gradient of f squared divided by the integral of f squared. And there, in fact, you also have that the eigenvalues of Laplacian correspond to non-trivial cohomology class of the underlying space, which is just the infinite projective space. And so Gromov conjectured that similar to how the eigenvalues of the Laplacian satisfy an asymptotic law, known as the wire law, these nonlinear analogs satisfy this asymptotic law, that whatever manifold we have, the minimal surfaces corresponding to the first topologically non-trivial family or second may be very different from manifold to manifold, from geometry to geometry. But as we take this limit to infinity, asymptotically, they only depend on the volume of the manifold. They should behave asymptotically the same way, just depending on the volume of the manifold and not on the geometry of the manifold. And this was a result that we proved for the case when k is equal to n-1 with Fernando, Marques, and Andre Neves. And more recently this year, we proved with Larry Guth in the case of one-dimensional cycles in 3 manifolds. So let me mention some consequences of this result. So the Y law that we proved with Fernando and Andre was then later used by Erie, Fernando, Marques, and Andre Neves to prove that for a generic metric on a Riemannian manifold, the space of minimal hypersurfaces is dense. And so the argument goes like this. So here you have manifold M, and say I make a tiny perturbation in the ball B to my manifold, which slightly changes the metric, which increases the volume slightly. Because I increased the volume slightly, that now changed the asymptotic distribution of these values of volumes of minimal hypersurfaces. And however, if no minimal hypersurface passed through this ball, then no minimal hypersurface felt that change. So that means that this small perturbation must have done something to minimal hypersurfaces. And the only way it could have done something if there is a minimal hypersurface passing through this ball. So this is how they proved that this asymptotic law implies that for a generic metric, minimal hypersurfaces pass through every. Later, with Antoine Song, Fernando and Andre strengthened this result to show equidistribution in the sense that not only they fill up the whole manifold, they fill it up in a certain uniform, equidistributed sense, which was the proof of that is basically you take the Y law, you take this limit, and you differentiate it with respect to different variations of metrics. It is technical because the width is only Lipschitz. It's not smooth, but nonetheless, you can make that work. Okay, and then the case with one cycles in 3 manifolds is that, so that case is a little bit special. Instead of closed geodesics, there you get something called stationary geodesic nets, which look like geodesic arcs meeting at vertices, and the sums of the tangent vectors has to be 0. So for example, when you're doing this procedure, you might get something like this instead of a closed geodesic medians meeting at 180 degrees. Actually, it turns out that you do not get that because of a recent paper of Chodorz and Montolidis in dimension 2. But in high dimensions, you may still possibly get that. And so in my work with my student Bruno Staffa and in Staffa's work with Xingzi Li, they proved analogous results for stationary geodesic nets in dimensions 2 and 3. That's right. So a priori, we have a theorem that in any Riemannian manifold, if you do this min-max procedure, then the limit will be necessarily a curve, a collection of, a graph, which consists of these geodesic arcs, and there may be vertices here. And if you sum the outward pointing tangent vectors, the sum will be 0. Now, it would be nice if that was actually an immersed geodesic, but it doesn't have to be. You can get some strange pictures, which look something like that, for example. In dimension 2, very recently, Chodorz and Montolidis showed that that you actually get immersed geodesics. Okay, so this was about, so this was kind of motivation why law is interesting and useful. Now let me tell you a little bit about the proof and specifically more about my recent work with Larry Guth in the high codimension case. So the reason why high codimension case is different is because of the following crucial step in codimension 1 case. The way we proved this result, one of the things we did is we cut our manifold into small pieces, and then we constructed optimal sweep outs on each of the pieces, and then we had to arrange them all together, put them all back together. And so here you have a very good sweep out on the left side, and a very good sweep out on U2. So these are families of relative cycles. So they can have boundary, but their boundary has to lie in the boundary of the region. And now we would like to somehow glue them all together into a continuous family of cycles in their union. And that means that we have to add something in the interface between the two, because right now on the top, they're not cycles. They have, so they're relative cycles in U1 and relative cycles in U2, but they're not relative cycles in the union of U1 and U2 because they have boundary in the interface. So here, this green pieces, sorry, this red pieces are gluing them together. And we have to do it in a continuous way. And we have to do it in a way that doesn't add much volume to the family. And in the case of codimension 1, it's pretty, you don't have a lot of choices. Basically, you have exactly two choices. Either you glue these two things by putting the red connecting tissue here, or you do it in the complement. So there are exactly two ways of doing that. And the volume, because we are looking at cycles with mod 2 coefficients, the volume will be bounded by the volume of the interface, and that will be small when the volumes of our cycles is very large. Compared to the volumes in U1 and U2, the volume of this boundary will be small. And then we have to repeat the same thing in the higher codimension case. It is trickier, because here you actually have infinitely many choices of how you want to connect up things on the left to the things on the right. And the problem is twofold. First of all, if we had a good bound on the boundary of these cycles, right? So this is the boundary interface, and this is various relative cycles touching it. Now, if there aren't that many points, then we have this family of points moving in the square, and we need to fill them in a continuous way and in a way that controls their size. So this is a parametric isoperimetric problem. Instead of just filling one boundary, we have to fill a whole family of boundaries, and we have to fill them in a continuous way, and we have to fill them in a way where we have good control on their volume. So that gives rise to the parametric isoperimetric inequality problem. But unfortunately, we may not even have that. We may have that the size of the boundary is very large. We may have many, many points. So we know that the volume of the cycle inside is controlled, but that doesn't give us any bound on the size of the boundary of the cycle. However, there is a trick that you can do, which is the co-area inequality, right? So imagine, for example, that this is your set, and then you have a, something like this. So if you look at this cycle, it has a very large boundary here. So there's this very windy spiral. But if you move a little bit to the left, then you can cut it here and there, the intersection will be small. So co-area inequality tells us that if you have control on the volume of what's inside, then by moving this wall, you will be able to find a point where the intersection is small. The plan is like this. You have this collection of moving cycles. And so now we start cutting it with this wall by moving it back and forth so that the intersection is small. And we have to somehow do it in a continuous way. And once we're done, we will have a picture where the boundary that's moving in the wall has controlled size, and then we can prove parametric isoperimetric inequality, and then that will imply the Weil law. So the problem basically breaks down into these two pieces. One is the parametric version of the isoperimetric inequality, another parametric version of co-area inequality. And we proved in the paper with Larry that if you prove these two conjectures, then that implies the Weil law. But so far, we've only been able to prove these two conjectures in low dimensions, which gave us the Weil law for one cycles in 3 manifolds. And the methods are almost there. I think it should work. It's just, there are some ad hoc things that work very nicely in these dimensions and become somehow more technical in larger dimensions. But I think it should be true. And So the parametric isoperimetric inequality conjecture can also be stated in this form, similar to the isoperimetric inequality that I stated in the beginning. That now, instead of one submanifold in Rn, we have a continuous family of submanifolds in Rn. And then we would like to find a continuous family of manifolds with boundary that are fillings of this family, and so that their volume is controlled. The key difficulty here is to make the constant in front of the volume here, this should be volume phi of x, not depend on the dimension of the parameter space. It's not too hard to prove this result where this constant depends on the parameter space in an exponential way, where this is something like 2 to the power of p, where p is the dimension of x. But the challenge is to prove something better than that, and ideally for this constant not to depend on the dimension of the parameter space at all. Any questions so far? I'd like to mention a third situation where a close relative of the isoperimetric inequality, the filling radius inequality, plays a role, and the methods are somehow very much reminiscent of the methods in these previous two episodes. So this is a question about how scalar curvature controls topology of a manifold. So if you have a manifold, then its shape is described by the Riemann curvature tensor, and it's somehow very large. Gromov calls it a monster of multilinear algebra. You can tame it a little bit by taking a trace and getting a Ricci curvature, and then you can take a trace of that, and then you'll just get one number, scalar curvature. So that number loses a lot of information about the shape of a manifold. However, it still has some non-trivial information. In particular, one geometric property that it has is that it controls the size, the volumes of balls in your manifold on a small scale. So there are two filling radius inequalities. One from the late 70s, early 80s, due to Shane Yao and Gromov-Lawson, is that if you have a three-dimensional manifold with positive lower bound for scalar curvature, then any curve, so this is a manifold M, three-dimensional, and any contractible curve can be filled with a minimal surface which doesn't lie far away from its boundary. It lies at most, if say scalar curvature is greater than 1, then it lies at most at the distance 2 pi. In fact, 2 pi is not a sharp constant. There's a slightly sharper, slightly better constant. And that has interesting implications for the geometry and the topology of this manifold. And recently, Chodesh-Mantoulidis and Gromov simultaneously, I think Chodesh-Mantoulidis first proved the result in dimension 4, and then Gromov and Otis and Chow proved the 5-dimensional case, proved a similar result in these high dimensions, slightly more technical. So if you have a manifold with trivial higher homotopy groups, you look at dimension 2 submanifolds in the universal cover, their filling radius will be bounded. Right? So the universal cover may be an infinite manifold, so there is no reason a priori why the filling radius has to be bounded. And so the idea is that if you have this n-2 submanifold, and now you look at the filling of that submanifold, then you can consider a certain minimization problem for a certain functional, which they call the mu bubble functional. And then you will obtain a minimizer for that functional somewhere a little bit inside the interior of the filling. So let me call it sigma tilde. And it turns out that if you pick this functional correctly, then the sigma tilde will have many properties of manifolds with the same scalar curvature bound as the original space M in which you're located. So if this was dimension 5, now we have this three-dimensional manifold, which behaves like a manifold with positive scalar curvature. And for manifolds with positive scalar curvature, we know that they're somehow small. So this is my result with Davi maximum from 2021, that you can foliate this sigma tilde by surfaces whose area, diameter, and genus are all controlled. So there you can think of this sigma tilde and you can map it into a certain graph. Fibers of that graph will be small. They will have small diameter, small area, and even small genus. So this sigma tilde can be very large, but if you look at it from far away, then it will look like a graph. It will look kind of one-dimensional. And this property implies that this sigma tilde can actually be filled in a small amount of.
Sorry, what is dimension of M?
So this gives this filling inequality, which in turn has nice topological applications. So, for example, you can use it to classify manifolds with positive scalar curvature with some mild conditions on their homotopy groups. I mean, some connectedness conditions. So if you have a four-dimensional manifold with pi2 equal to 0, or if you have a five-dimensional manifold with pi2 and pi3 equal to 0, then in fact, a finite cover of that manifold is homotopy equivalent to either a sphere or a connected sum of Sn minus 1 cross Sn. So there you actually have cross S1, you actually have quite few manifolds like that. And the main tool is that we can analyze the universal cover of this manifold, and this filling radius will give us information on the number of ends of this universal cover, and then we can use results of Stollings and others who studied the number of ends of the universal cover and group actions to tell us that this, in fact, can only be this. That's right, M is three-dimensional in our result with Davi. Right, and I think this is it.
Yeah, thank you very much. So I don't know if there are any questions from the room. Yes? Oh, wait a second. I'm just gonna give this to you.
Thank you for a very interesting talk. I was just wondering if you can say a few words how this nonlinear while law implies this equidistribution results that you mentioned.
Mm-hmm. So if we look at the while law, let's take the codimension one case. So we're looking at the p width of M divided by p to the power of 1 over n, and is equal to some constant times the volume G. And then we can start considering different variations of the metric. And in fact, Marques, Neves consider conformal perturbations of the metric G. And if we now differentiate the whole thing with respect to T, then here on the left, basically, we will see the derivative with respect to the variations of the metric of the volume of the minimal surface. So we'll see how the volume of the minimal surface changes with respect to that variation of the metric. And on the right, we will see the derivative of the volume of the whole manifold. And basically, what will come out of this is exactly the equidistribution kind of statement. So the equidistribution statement that they prove is that they have a sequence of minimal hypersurfaces that the sum of over sigma I f over volumes of sigma I. No, I think, right, I think it's, right, so limit as p goes to infinity of, and here we have, let's write sum of the volumes, so sum of the integrals of f on sigma p, and here over the sum of the volumes of sigma p. So where and so where this is true for every smooth function, right? And so now you can pick some specific collection densely populating the space of functions, and for each such, so you can pick some countable collection phi, which will correspond to your conformal perturbations, and then you can prove for these phi's that this difference, what will come out when you take the difference here, that when you take the derivative here, that this difference will be small. But there is quite a few very non-trivial technical details, which in particular have to do with the fact that this is only Lipschitz maps. So you have to select these points carefully and use Sart's lemma, infinite dimensional Smale-Sart's lemma a few times, and some other things.
Okay, thank you very much. Let's see, maybe there are some questions online. If you have some questions, maybe ask them. You can ask them in the chat. I'm saying this for the online.
Yes,
there are no
I think
other
I answered this one already.
Yes, exactly. You already answered that one. So it's time to congratulate you again.
Thank you.
Thank you.